All right, welcome, welcome, welcome. You should have a new packet. Yay, new notes packet. All right. This whole unit is talking about exponential functions. And exponential functions I really like. They're very interesting, but they're also like real life. So we're going to talk about exponential functions. And we're going to tie in some logistics functions. We have lots of applications because this is like real math, which I think is really interesting. So we get some really good applications in this unit, which are important. An exponential function is when we have an x in the exponent. X in the exponent makes it an exponential function, okay? Say that over and over. And a basic function looks like f of x equals a times b to the x. So the x is in the exponent position. And then we have our base b. And there's this multiplier out in front, and that multiplier can stretch or shrink our exponential function. Do you know what an exponential function looks like? Good, yeah. Exponential functions grows quickly. And so that is the basic function, something like 2 to the x. Has anyone been to Six Flags Magic Mountain? Yes? Okay. One person. Okay. So the Six Flags Magic Mountain, they have a ride called Superman. And the Superman ride, it's really a stupid ride. Everybody, like 30 people sit in this cart that has like 3 rows of 10 chairs each, and you all, pull down the thing, and then the hydraulics just compress and compress and compress and compress. And all you do in your 3 rows of chairs is you sit there, and then all of a sudden it like shoots you straight out, and then you just turn and go like straight up. So it's like Superman flying like to the moon, but that's what it does. Well, the Superman ride is the equation y equals 2 to the x. It is an exponential function. And if we wanted to graph any exponential function, we can very easily take this function and do a little XY chart. It is super easy to do, and I just always like to start with an XY chart because it reminds us where graphs come from, right? I'm going to choose -1, 0, and 1 for my x values. Always a good 3 points to choose. And so what I'm going to do is I'm going to take my 1 and I'm going to plug it in place of the x. So that would be 2 to the first power. What is 2 to the first power? No, I'm starting with 1. So that's just 2. And then I'm going to go to my 0. And if I plug in a 0, so that'd be 2 to the 0. What is any number to a power 0? 1. Any number to a power of 0 is 1. Yeah? Okay, this is why I do this, because it's important to remember that. And then, now, Brody, 2 to the -1. What does a negative exponent do? It flips the fraction. Yeah, so 2 flips, and it becomes 1/2 to the happy first power now. So it flips your fraction and becomes 1/2. Which, of course, if you wanted to use your calculator, you could, but I like to remind us that we do have brains. So 2 to the -1 gives us 0.5, which is, of course, 1/2. And in case we're not convinced, 2 to the 0 is 1. It's defined that way. It has to work that way. So those are 3 easy points. So -1 up 1/2, 0, 1, and then 1, 2 are our basic 3 points for this function 2 to the x. What if I used like -2 for the x? That'd be 2 to the -2. What happens there? 1/4. It does become 1/4. And if I had -3, 2 to the -3, 1/8, yeah. So like 2 cubed is 8, but we put it over a 1, so it'd be 1/8. And so what happens here is as we move to the right, or sorry, that's left. As we move to the left, our fraction is just getting smaller and smaller and smaller, right? So negative 1/8, or not negative 1/8, but 1/8, 1/16, 1/32, 1/64, etc., etc. Is it ever going to get to 0? No. And because it's never going to get to 0, we have a horizontal asymptote right here. In this case, at y equals 0, we have this lovely little boundary line that our exponential function isn't going to cross. It gets very infinitely close to it, but it does not cross it, and it just grows as we move to the right. And so this is the Superman ride, and I call this the Superman graph. So anytime I'm like, what shape is it? And you're like, Superman! And that's what it is. It's just the Superman ride. So I call it Superman going to the moon. This is called exponential growth. It's exponential growth because as we move to the right, our values are growing. They are getting bigger and bigger and bigger really, really quickly. We would really like our money to grow this quickly. It seems like you never get there. All right. That is with a base of 2. What happens if we have a base of 1/2? It does. It gets smaller and smaller and smaller. So this is actually exponential decay. Again, I can very easily create a little XY chart with some easy values, -1, 0, and 1, if I'm ever unsure. It's just such an easy thing to do. So 1/2 to a -1 power. What does that -1 power do? It flips the fraction and it becomes 2. All right, and then if we have 1/2 to a 0 power, what is it? 1, always, always. And if I have 1/2 to the first power, what do we get? 1/2, yeah. So I'm graphing -1 up to 0, 1, and 1, 1/2. And so this is called exponential decay. It's decaying, getting smaller and smaller. And again, it's going to be, 1/2 and then 1/4 and 1/8 and 1/16 and 1/32. Again, it's getting closer and closer and closer to 0. So we have a horizontal asymptote. Again, y equals 0. This boundary line that we're going to get so close to, but never really touch. And then it just grows. As x moves left, we are growing. And so this is like Superman coming in for a landing. That's how I describe it. Okay. So this is exponential decay. It's decaying. The y values are getting smaller. And again, exponential decay. This is radioactive material. This is Chernobyl. Every 373 years, or whatever the half-life is, you have half as much radioactive material. And that's, something. So in the first 300 years, it decreases by half. That's a lot. And then it's half of that. And then it's half of that. And then it's half of that. So it's pretty interesting. Let's see. So this is exponential growth and exponential decay. We are going to make sure that we can graph all of these functions. And she's asking a lot. Let's look at number 1. We have f of x equals 3 to the x. And again, I'm going to say, hey, let's just really easy make a little xy chart. And I'm just going to use -1, 0, and 1. What is 3 to the -1? 1/3, good. What is 3 to the 0? 1. And what is 3 to the first? 3. So now I've got easy ordered pairs to graph. -1, 1/3. 0, 1, and 1, 1, 2, 3. Does it have a horizontal asymptote? Yes, it does, absolutely. It still has that horizontal asymptote. Those fractions are going to get closer and closer and closer to y equals 0, our horizontal line there. So it is, oops, I missed my points there. There we go. Is this exponential growth or exponential decay? Growth. All right. Because it is increasing as we move to the right. All right. I care about the asymptote. Y equals 0 is our horizontal asymptote. HA is how I abbreviate it on my worksheet you're going to get today. And I care about the domain and range. Domain, remember, is how far left and how far right the graph goes. So negative infinity to positive infinity for the domain. It goes forever to the left and forever to the right. What's the range? Yeah, low to high. Very good. So what's our lowest y value? 0. Included or not included? Not included. So parentheses. So our lowest y value would be 0, but not 0. Not equal to 0. And then what's our highest y value? Infinity. So 0, infinity. Perfect. Beautiful. And those are the things I care about. Is it an increasing or decreasing function? Increasing. It's absolutely going uphill the whole time. Okay? Increasing. All right, super. Turn the page. Let's talk about the natural base exponential function. So you have a button on your calculator. The natural base is base E. And E is a number like pi. E is an irrational. E is an irrational number with an approximate value of 2.71828. It is on your calculator. 1828. It is on your calculator. It is, yes, but we're going to use this one because typically we want e to some power. E to the x is in blue, so you can see e to the first power, if we wanted to, is 2.71828. Oh, you can't see that. Just kidding. There you go. E to the first power. I think that one works as well, just e to the first power, so same thing. But it's right there above the ln. It looks like in, but it's an L. Okay. So there's our e that we're going to use most of the time, right there in blue. Okay. So I have a phrase because I have a phrase for everything. What is e? What is e? You're going to say not quite 3. Not quite 3. Because 2.7 is not quite 3, right? Okay. Because I am going to make you graph these by hand, but of course, can I graph 2.71828? No, that's silly. But can I graph not quite 3? Yeah, okay. So what is e? Not quite 3. Very good. Okay. So this is the natural base number. It's called a natural base number because it actually occurs in nature. We watched a whole video on it in 8th grade math about it. They drew our Fibonacci spiral. This is related to E, all right? And it is just really a pleasing number. It occurs in nature all the time. It's very cool. And it's a number much like pi that just naturally occurs. It's just weird. Well, it's the ratio. Well, actually, that's phi, but there's a few numbers. But you guys are learning all these cool numbers. You have like now you've got like 0, 1, 2, e, 3, pi, 4, pi. So there's all these other numbers that are fancy that just happen to appear. But I'll try and find a video about where that comes from if I can remember. And so base E, because we know that what is E? Not quite 3. We can actually graph it in much the same way. So if I want to graph e to the x, so again, I can do a little xy table, and I can use -1, 0, and 1, and I can plug it in. Well, let's see. So if I plug in e to the -1, well, that's 1 over e. So that's 1 divided into not quite 3 parts, okay? So 1 divided by e is not quite 3 parts. It's not quite 0.33, all right? All right? So, and then here I have e. What's e to the 0? 1. And what is e to the first power? 2.7, or not quite 3. So, -1 and 1 divided into not quite 3 pieces, so that's about there. 1/3-ish. And then we have 0, 1 again, and then we have 1, not quite 3, so just under 3. And there we have our natural base exponential graph. Does it have a horizontal asymptote? Yes, it does. It has that horizontal asymptote, which I want you to draw. So again, it has that horizontal asymptote. And is it exponential growth or exponential decay? Growth. Yeah, it is exponential growth, again, because that base value is a number bigger than 1. So if that base is bigger than 1, it's going to grow. If it's between 0 and 1, it's going to decay. All right. And what is E? Not quite 3, so that's a number bigger than 1, so it's going to grow. Our horizontal asymptote, again, is at y equals 0. What's our domain? Negative infinity to positive infinity. What's our range? 0 to infinity. Perfect. Okay, great. And so we have these natural base functions that we can graph as well. All right, are you good so far? All right, turn the page. As a reminder, we can shift. You got a negative in front. What's a negative in front going to do to our Superman curve? Yeah, it flips it vertically, all right? You have pluses and minuses. It's going to shift it left, right, up, or down, all right? So we're going to practice graphing some with transformations. We're going to turn the page. And my directions that we're going to do, my directions say graph the core, then shift. Okay, graph the core, then shift. So what I'm going to do is I'm going to write you a really generic format here. This is number 9. I turned the page twice, so yeah. All right. Here's a really generic format here. F of x equals a times b to the x minus h plus k. So f of x equals a times b to the x minus h plus k. Right here, the a times b to the x, this is what I call the core function. And so we're going to create a real simple table of values for that core function, real easy to do, and then it gets shifted h units left or right and k units up or down. All right, so it's real easy to see. So here I have, what's the a on this function in number 9? 3. Oh, what's the b?
1.
So it's actually 1 times 3 to the x minus 1 minus 4. So the a is actually 1, and the b is the 3. So just in case you're curious, I like to point that out. So I'm going to take this core right here. So here's my core function, which is really just 3 to the x. And I'm going to do a little table of values right below here with just 3 to the x. I can use -1, 0, and 1 like I've been using. What is 3 to the -1? 1/3. What is 3 to the 0? 1. What is 3 to the first? 3. Perfect. So I have some great core values I can pull out here. So -1, 1/3, 0 up 1, and 1 up 2 up 3. All right. This is my core function, and I'm just going to make it a dotted graph. And then I'm going to use my second color, and this is going to get shifted. What does x minus 1, what does that minus 1 do to this graph? Yeah. So I'm just going to draw an arrow and go right 1, and what does the minus 4 do? Down 4. And so I'm just going to write it just like that, right 1, down 4. And I'm going to take my 3 points that I've got, and I'm just going to count right 1, down 1, 2, 3, 4, and plot the new point. Right 1, down 1, 2, 3, 4. Take my third of the way point, go right 1, down a hole, down a hole, down a hole, down a hole. So now let me ask you, we had a horizontal asymptote that's connected to the graph. Where is that horizontal asymptote now? Yeah, it's minus 4. That shift, that horizontal asymptote is always whatever that k value happens to be. So our horizontal asymptote is y equals negative 4. And so I'm going to go ahead and draw that in there because I don't want to cross it. It's a boundary line. And then I can draw my exponential growth curve. What's the domain? Good. Negative infinity to positive infinity. What's the range? Excellent. Negative 4 to positive infinity. Good. Questions on that one? All right. Let's look at number 10. What's the A? Negative 1. You can imagine there's a negative 1 right there. Negative 1 times the 1/2 to the x. What's the H? 0. X minus 0. You can imagine there's nothing there, so you can fill in with a 0. Any plus or minus, so you can fill in with a 0. All right. All right. So again, I'm going to graph the core, which is this a times b to the x. So there's our core function right there. And I'm just going to do a little table of values. Negative 1 times 1/2 to the x. Negative 1, 0, and 1. All right. Let's see. Negative 1 times 1/2 to the negative 1. Order of operations. What do we have to do first? The parentheses and the exponent. Yeah. So this thing right here, what is 1/2 to the negative 1? 1/2 to the negative 1 power. Which is 2. Yeah, it flips your fraction. That negative exponent flips your fraction. So it just becomes 2. So this is negative 1 times 2, which is negative 2. If I plug in a 0, negative 1 times 1/2 to the 0. What is 1/2 to the 0? 1 times negative 1? All right, then I have negative 1 times 1/2 to the first power. Again, you got to start with your exponent. What's 1/2 to the first power? It's 1/2, and then with a negative, negative 1/2. All right, good. All right, so a couple things here. First of all, is this exponential growth or decay? I know it's decay because of the 1/2. That's a number between 0 and 1. It's going to be a decay function. So this is Superman coming in for a landing, but it's got a negative in front. So this is Superman coming in for a landing, but it's flipped upside down. So let me see what happens here. We've got negative 1, negative 2, 0, negative 1, and then 1, negative 1/2. So that Superman graph got flipped upside down, and so this is looking like this, where it's Superman coming into a landing, but coming in from below because of the negative. How does this graph get shifted? Yeah, just up 2. So I'm going to take each of these points and go up 2, up 2, and up a hole, up a hole. What happens with our horizontal asymptote?
It changes to 2.
Yeah, it's up at 2. Y equals 2. So our horizontal asymptote is y equals 2. And then I can draw in my curve, just like that. So this is a negative Superman coming in for a landing. What's the domain? Tricky, tricky. What's the range? Negative infinity. How low does it go? Negative infinity. How high does it go? 2. So negative infinity to 2. So that one gets flipped around. Questions on that one?
Yeah, I have a question.
Yeah.
Why is the other side of it like 2 if it gets so close it doesn't touch it? Is that just like where it could possibly go?
Up to, yeah. And so that's the parenthesis, which means...
Yeah, I get that, but like, because it never touches 2 though. So is that just like the highest it could ever be? Is like...
Right. An infinite amount of time.
Okay.
We're still really, really close, but not actually touching. So, yeah. Theoretically, it gets to 2.
Okay.
All right, let's see. I want to try the page. I'm going to change some of these. How are we on time? Okay. I don't want to do that one. Let's not do that one. Let's do, f of x equals 2 times e to the x minus, I don't know, 1 minus 4. All right. 2 times e to the x minus 1 minus 4. What's our core function? Yeah, 2 times e to the x. There's our core. So that's what we're going to plot first, and we can do that with a little xy chart pretty easily. Negative 1, 0, and 1. Will you tell me, is this exponential growth or exponential decay?
Growth.
Growth. How do we know?
It's more than 1.
The e, the base is bigger than 1. So e, what is e? Not quite 3. Yeah, okay. So it is exponential growth because it's not quite 3. So that's a big. I'm going to just, I know the shape is like this, so I'm going to just use 0. 2 times e to the 0. What is e to the 0? 1. Times 2 is 2. Perfect. And then 2 times e to the first. What's e to the first? What is e?
2.7.
Not quite 3. So what is 2 times not quite 3? Yeah, 5 point, I don't know, 8 something. Yeah, who knows? Not quite 6. All right. And so we could graph that. We've got 0, 2, and then 1, not quite 6. 1, 2, 3, 4, 5, 6. So we're going to be under that 2.7. What is that? I don't know what it is. Let's see. You could check it if you want. 2 times e. I'm just curious now. Oh, 5.4. Yeah. So 5.4. All right. And I know that it's exponential growth, so we know that it's got this Superman shape like that. And now we can go ahead and shift those points. How do we shift them? So what? Right 1 and then down 4. Yes, right 1 and down 4. So I'm going to take my easy point. I'm going to go right 1, down 1, 2, 3, and 4. And I'm going to take my weird point and go right 1 and down a hole, down 2, down 3, down 4. And what happened in my horizontal asymptote? So it's at y equals -4, yeah. So I want to draw in that horizontal asymptote first. 1, 2, 3, -4, yeah. And then I can draw my Superman growth curve. So something like that. Can you check these on your calculator? Absolutely. But we're graphing by hand because it's good to know how to do basic ones. All right, what's the domain? Negative infinity to positive infinity. And what's the range? -4 to positive infinity. Beautiful. Great. Do you want one more? Or are you okay?
I'm good.
Okay. All right, then I'm okay with that. We have a little worksheet